My name is Rich Townsend. I'm going to be telling you about modeling stellar structure and evolution. This is an area I've been involved in for probably a couple of decades now. I still don't fully understand it. Stellar structure and evolution is one of the oldest sort of branches of astrophysics, and it's one that, on the face of it, is relatively straightforward. A lot of the physics is 19th century physics. A lot of the equations we solved are just simple, one-dimensional, ordinary differential equations. For the most part, getting into stellar astrophysics or stellar structure and evolution is pretty straightforward. Something that's kind of different than many other branches of astrophysics is as you actually start seeing how stars change over their lifetimes, how they evolve, there's a lot of emergent complexity that's really not apparent when you just write down the basic equations. And I guess the interesting part for me of studying stars comes in trying to understand this emergent complexity and to develop a sort of cogent narrative that sort of sits well with one's physical intuition. So I'm going to start out at the very beginning. Actually, even before I start out, I'm expecting lots of interruptions and lots of great questions because we've already had a demonstration earlier on today that there are lots of great question askers in the audience, so please do stop me to quibble with absolutely anything. So I'm going to start out by actually putting up a provisional definition of what a star is. It seems kind of redundant, but there are actually a number of important words on this slide that really kind of hold the key to my claim that the interesting thing about stars is their emergent complexity. So a star is a self-gravitating gaseous sphere that at some point during its life shines via fusion of hydrogen. So in this simple sentence, there are a lot of interesting bits of physics. Firstly, let's start out with just the word star, a star. So we're talking about a single object. So a star is a singular object. It's a thing. It's not some sort of general concept like turbulence or, let's say, electromagnetic radiation. It's a specific object. We can go outside right now, look up in the sky and see one. Okay, so we're modeling a singular object, and a singular object held together by its own gravity. When we put together models for stars, we need to worry about self-gravity, the mutual gravitational attraction of different parts of the star. The sphere bit is kind of slightly less interesting. By default, when things contract under their own self-gravity, they want to form a sphere. This sort of subclause at some point during its life is interesting because the word life is in there. So we're not talking about biological life here, but life in the sense that stars have a beginning. They evolve, they change from how they were at the beginning, and they reach a final state, and then they end. So they're a phenomenon that's not only sort of compact in space, they sit at a specific point in space, but they also cover a specific sort of window in time. They have a beginning and an end. Here we've got the word shines, which means that stars pump out energy into their surroundings. They somehow generate energy inside themselves, and in fact, that's at least at some point in a star's lifetime, that's done by a fusion of hydrogen in the core, and then this energy is lost from the star through its surface. Basically, since stars live out in space, and space is cold and empty and dangerous and nasty, they're sitting in this sort of cold, hard vacuum, and they can't help but to radiate energy away into it and to lose energy. A star's life is really the struggle between losing energy into space and trying to replace that energy that was lost via this fusion of hydrogen. They can go on to fuse other elements, but at the bare minimum, if it doesn't fuse hydrogen, it's not even a star. It's maybe a brown dwarf or a planet. So just from looking at this sentence, we know we're talking about a singular object. We know to model this object, we're going to have to worry about gravity. We're going to have to think about the transport of energy by radiation and perhaps other mechanisms, because stars shine. The energy is moving from somewhere in the star, the core, up to the surface. We're going to have to think about nuclear reactions, and we're going to have to think about how the star changes over time. That just sort of sets the stage for how we're going to think about stars. What we're not going to discuss in this lecture and the one tomorrow are a couple of complicating factors that make stars even more interesting than usual. I'm not going to say anything about magnetic fields. I'm going to ignore the fact that probably the majority of the stars are actually part of binary or higher order systems. I'm going to pretend that stars don't rotate at all, because that makes things tricky, and I'm not going to worry about general relativity at all. In most cases, that's okay for stars, but even for the sun, if we want to model the advance of Mercury's perihelion, we have to take general relativity into account. So I'm actually going to pick up where Pascal kind of took us, thinking about the fluid equations. Stars are made up of essentially a plasma, maybe out in the surface layers, the ions and electrons in the plasma recombine, so it's actually more like a gas. But to all intents and purposes, I'm not going to really worry about the special properties of a plasma, and we're just going to treat a star like a fluid. And because it's a fluid, it must obey the fluid conservation equations. So here we have the momentum conservation equation written in sort of Newton's second law form. If you remember, this big D is the derivative following fluid elements. It's the Lagrangian derivative. So this is basically the MA term. And then on the right-hand side, we have forces due to pressure gradients, due to viscosity. And then here we've got a term that represents the force of gravity. So big phi is the gravitational potential of the star. And this gravitational potential, because this is self-gravity, comes about from the star's own mass distribution. Since we're going to be focusing on spherically symmetric stars, we can rewrite this equation in spherical symmetry, and we're also going to think about a situation where the star's not actually moving. If we look at our sun, we can see sort of small-scale motions of the fluid making up the sun, but for the most part, the sun's just sitting there. It's not really going anywhere. And that's great for us because, you know, if the star was expanding and contracting violently, or if it was just flying all over the sky, then it'd be difficult for life to develop here on Earth. Stars are around for a long amount of time, typically billions of years, maybe sometimes a little bit shorter, a little bit longer. But things happen slowly in stars. So in many situations, we can actually neglect any fluid flow in the stars, so we can neglect this acceleration term here. We can also neglect the viscous terms here, because it turns out the material making up stars really is almost completely inviscid. Sometimes if there's convection and we have to worry about turbulence, there might be some kind of sort of viscosity that comes about from turbulent motions, but at the molecular or sort of particle level, the viscosity of material in stars is almost negligible. So if we drop this acceleration term, drop the viscosity, and then rewrite things a little and do it in spherical symmetry, we end up with an equation that I'm sure many of you have already encountered if you've studied stars at all. This is the equation of hydrostatic equilibrium, and it really just states that sort of balance between the inward pull of gravity and the outward push of pressure forces, the pressure gradient in a star must match negative the density times the potential gradient. And this potential gradient really is just the star's own self-gravity. So basically, the inward pull of gravity is in balance with the outward push of pressure forces. This is what hydrostatic balance or hydrostatic equilibrium actually looks like in the sun. This is from a model of the present-day sun. So what I'm doing is I'm plotting the pressure gradients, dp dr, together with the other term on the right-hand side of the hydrostatic equilibrium equation, rho d phi by dr, and I'm plotting them as a function of radius in our model for the sun, and the radius coordinate is expressed in units of the sun's total radius, which is about 7 times 10 to the 10 centimeters. These two curves, the blue line and the dotted orange line, lie nicely on top of each other, which tells us our model for the sun is in hydrostatic equilibrium. There may be a little bit of discrepancy here, but that's probably because I've just done a crappy job of calculating the pressure gradient in Python, okay? Actually, in the model, hydrostatic equilibrium is satisfied very nicely. So we can see that the pressure gradient vanishes at the center of the star. It goes up to a large peak about 10% away from the center of our model, and then it goes down to a small value up at the surface. And this large peak here really is because just outside the core of the sun, that's where the self-gravity is kind of strongest. because we've got a lot of mass in the core. The distribution of material in the sun is quite concentrated towards the center, so there's quite a lot of mass in the core, and we're quite close to it. In writing down our equation of hydrostatic equilibrium, I sort of waved my hands and said, let's just not worry about the time-dependent term, that acceleration term. But really, how reasonable is that? Well, to get an idea of the consequences of neglecting that term, we can ask ourselves instead, if we went back to the original momentum equation and thought about what would happen if not the velocity term vanished, but the pressure support of the star vanished. Basically, if we took a star that was in hydrostatic equilibrium and could artificially turn off the pressure instantaneously. The equation of motion for the star is now just that the infalling acceleration of material is equal to the gravity, and the star would collapse down to a point on a characteristic timescale that we call the dynamical timescale, and it comes out to a very good degree of approximation to be the square root of r cubed over gm, where big R is the star's radius, and m is the star's mass, and g is obviously the constant of gravitation. Now, in reality, if we turned off pressure like this, the star wouldn't collapse down to a point. We would get interesting stuff happening, like maybe the formation of a neutron star or a black hole, but let's not worry about that. So the dynamical timescale is basically the how fast a star would react if we suddenly turned off all the pressure, and we can play the game the other way around and say, how long would it take for the star, let's say, to double its radius if we turned off gravity and allowed it to explode? And we get out actually more or less the same scaling, square root of r cubed over gm. And if we actually plug in numbers for the sun into this equation, we find the dynamical timescale comes out to be about an hour. 1 hour. Very short. Okay, and in fact, that 1 hour, it's kind of another way of thinking about it is it's just the sound crossing time in the sun. It's how long a sound wave takes to get from one side of the sun to the other. And what that tells us is that if we look at the sort of sun and average it over timescales that are significantly longer than 1 hour, this dynamical timescale, then over those long time periods, the departures from hydrostatic equilibrium in the sun are going to be negligible. Basically, if for some reason something kicks the sun out of hydrostatic equilibrium, it'll only take an hour to get back into hydrostatic equilibrium. So over long time scales of, let's say, a year, a century, a millennium, a million years, a billion years, over those longer time scales, the sun can be considered to be in perfect hydrostatic equilibrium. It's only when we worry about processes shorter than the dynamical timescale that we ever have to think about departures from hydrostatic equilibrium. And in practice, there are very, very few points during a star's life where it ever significantly departs from hydrostatic equilibrium. Okay? Okay, so let's now talk a little bit about gravity in the star. So to calculate the gravitational potential from a distribution of mass, we can use Poisson's equation. And in spherical symmetry, we can rewrite this after, have I done this right? Yeah, I have. We can integrate it once to get Gauss's law for gravity. So basically, the potential gradient, which is basically the scalar gravity, is just gm over r squared. And this m here is a new variable we've introduced, which we can call the enclosed mass, or maybe a Lagrangian mass coordinate. At every radius in the star, we can define m to be the amount of mass of the star that lies interior to that radius. So it's basically the integral from the center out to our position of the volume element times the local density. And we could also write this integral equation as a differential equation. And when we're dealing with constructing models of stars, it often turns out to be more useful to use lowercase m, this mass coordinate, to sort of label where we are in a star than the radius. Because during its evolution, a star can expand and shrink down by many orders of magnitude, but unless it's actually losing mass, its overall mass remains the same. And if you follow a part of the star with the same mass coordinate, you'll basically be following the same material. So let's take a look at gravity in our model for the present-day sun. This is a plot of both the gravitational potential scaled to gm over r, and the potential gradient, which is just the scalar gravity, as a function of radius. Just as we kind of intuited from the hydrostatic equilibrium plot, the gravity vanishes at the center of the model, but rises up to a peak just outside the sort of core regions, and then drops off. And as we get out towards the surface, it's sort of dropping off like 1 over r squared. The gravitational potential is negative everywhere. It's, by definition, we take it to be, I think here I've taken it to be 0 at the surface of the star, and it drops down to a sort of potential well right down at the center of the star. So based on our solution to Poisson's equation, we can put together an estimate for what the gravitational potential energy of the star is. And this will turn out to be quite useful when we're thinking about what energy sources a star can draw upon to sort of provide that or replace that energy it's radiating away into space. Let's define little omega to be the specific gravitational potential energy. That row actually shouldn't be there, should it? No. I'm not going to edit it now. Forget that row's there, okay? So minus g times the mass coordinate divided by radius, that's the gravitational potential energy per unit mass. So we can get an expression for the total gravitational potential energy or total gravitational binding energy of the star by just integrating omega over the mass distribution of the star, and that gives us big omega, which is just the integral with respect to mass coordinate of gm over r. And we're taking that integral from the center of the star up to the surface of the star, which has mass coordinate equal to the total mass of the star. And it's important to realize when evaluating this expression that the radius appearing in the denominator is an implicit sort of function of m. We have to know, given a mass coordinate, what the radius of the material at that mass coordinate is. So for the sun, which is indicated with this fried egg here, the total amount of gravitational binding energy of the sun is about 6 times 10 to the 48 ergs. So that's how much energy you would basically have to inject into the sun in order to scatter its material to infinity. Yeah.
So I think there's not like a hard surface to the sun, and so you have to have some way of
So that's correct. There isn't really a hard surface to the sun, but when you reach the very, very outermost layers, the rate at which the density and the pressure are dropping becomes quite precipitous. In the very superficial layers of the sun, the pressure scale height, so the sort of E-folding length for the pressure to drop away, and likewise for the density, is on order of about 1,000th of the sun's radius. So it's almost as if the sun has a hard edge out as its surface. It's not completely hard, and there's always a small amount of mass further out. And in fact, if you keep going above the sun's surface, you never actually run out of mass because you start going out into the solar wind. And if you keep going out through the solar wind, eventually you reach the interstellar medium. So really, you know, in a sense, you can never go far enough away from a star that you get to a vacuum that really has nothing in it, because, you know, the universe is just not empty like that. But effectively speaking, when we get out into the superficial layers of, let's say, the sun, the layers that we can actually see using visible radiation, all of the material above those layers makes up maybe just 1/1000th or less of the sun's total mass. So there's just so little stuff out there that we can effectively conclude that we have reached the edge of the sun, okay? Practically speaking, how one defines the edge of the sun really depends on what wavelength one's talking about. And usually we define the edge or the surface of the sun to be the position of the layers from which most of the sun's light emerges from. Basically, the layer of the layer at which radiation last interacted with matter. Okay. Okay, so we've encountered a couple of equations now. We've looked at the equation of hydrostatic equilibrium, and we've looked at Poisson's equation for the self-gravity. Let's briefly talk about the equation of state for stellar material. So this is basically the recipe, the formula that tells us about the thermodynamic behavior of the material making up the sun. And there are many different ways of representing equations of state, but we're going to focus mainly on basically coming up with a prescription for how to calculate the pressure of the material in the sun if we happen to know its density and temperatures. You tell me a density and temperature, and we can use the equation of state to calculate a pressure. The material making up a star can be viewed as a three-component fluid, and these three different components don't interact with each other directly. So basically, we can take the partial pressures from these three components and add them together to get the total pressure exerted by stellar material. And these three components are pressure coming about from ions, which is basically anything with a nucleus and maybe some electrons left orbiting. In fact, it doesn't even have to have any bound electrons left. It's a combination of ions, bare nuclei, and atoms. So anything that's got a nucleus counts as an ion. Then there's the pressure from free electrons. So these are electrons that in cold material, they would have been bound to atoms, but because stars are hot, they've been ionized by the kinetic energy of the gas, and they're basically floating around free in between the ions. And then the final component to the pressure exerted is photons, radiation pressure. So to calculate the total pressure, we just need to calculate the ion pressure, the electron pressure, and the photon pressure, and then just add them together. The formula for radiation pressure is very straightforward. So long as we're in a well sort of thermalized medium where the mean free path is very short compared to typical temperature scales, then the radiation field is isotropic, and the radiation pressure is just 1/3 times the radiation constant times temperature to the power of 4. For the most part, in almost all stars, apart from maybe a couple of special cases like neutron stars, the ions, and remember that includes neutral atoms as well if they're able to exist, behave like an ideal gas. So the ion pressure can be just written as the number density of ions, so this is just the number of ions per unit volume, times Boltzmann's constant, times the temperature. And that's pretty straightforward. The electrons are where most of the pain comes in dealing with the equation of state for stellar material, because depending on what sort of object we're looking at, the electrons can behave as an ideal gas, or they can behave as a degenerate gas where the Pauli exclusion principle comes into play in basically affecting the pressure that they exert. And in some situations, the electrons can actually, there are sort of effective thermal motions can approach relativistic speeds, so we need to take in special relativistic corrections into account as well. So we've got three choices here. At relatively high temperatures and low densities, the electrons will behave like an ideal gas with a pressure just given by the electron number density. And remember, this is free electrons times Boltzmann's constant times the temperature. At higher densities and or lower temperatures, we will transition over to the degenerate non-relativistic limit, which is basically where the electron pressure goes as the 5/3 power of the electron number density with no dependence on temperature. And at the very highest densities, this exponent will actually transition over to 4/3. And these are just limiting cases. In fact, to get the proper expression, you have to do the full Fermi-Dirac statistics and mess around with distribution functions and stuff like that. So I've only given you the limiting cases here. So it turns out for the sun, this is a pretty reasonable expression. And in fact, for most stars that are still burning hydrogen in their cores, apart from low mass stars, this works pretty well for the electrons. We have to worry about these two when we're thinking about stars that are turning into red giants, and when we're thinking about white dwarfs, which are kind of the degenerate remains of low mass stars. So let's take a look at those partial pressures in the sun to get an idea of where we stand. So this is a plot of the three different partial pressures: the radiation pressure, ion pressure, and free electron pressure. And I've actually done it as a function of 1 minus the mass coordinate divided by the total stellar mass. And this is a nice way of plotting quantities in a stellar interior, because it tends to sort of magnify the surface layers. So if we're out here, for instance, at about 10 to the minus 12, that basically means that all but 1/1000th of a billionth of the star lies interior to that point. So we really are out into the very superficial layers. If we look at these curves, the first thing to note is that the blue curve is on the order of 3 orders of magnitude or more, but below the other two curves. So in the sun, radiation pressure is completely unimportant, okay? And that applies to stars with masses similar to the sun or lower masses. As we go up to more massive stars, let's say a 5 or a 10 solar mass star, that situation actually changes around. And for maybe 15 solar masses and above, in fact, radiation pressure is the dominant pressure term in the equation of state, and therefore is the pressure primarily responsible for supporting the star against the inward pull of gravity. But not in the sun. The sun radiation pressure can be largely ignored. And if we look at the ion and electron pressures, we can see that they're very comparable throughout most of the star. But as we get out towards the very superficial layers, the electron pressure starts to drop away. Now, the electrons are behaving still like an ideal gas. There are no degeneracy effects here. So what's going on here? Why do we run out of electron pressure support towards the surface? Any thoughts? That's right. Not as ionized. So the solar wind does carry away a little bit of mass, but the sun's wind, the mass loss rate is around 10 to the minus 14 solar masses a year. So it really has a negligible effect on the sun's structure. In fact, even over the sun's whole lifetime, it'll only lose, 1/10,000th of its mass. So in fact, Aurora hit the nail on the head. This is an ionization effect. As we go out to these very, very superficial layers, in the case of the sun, its surface layers are so cool that hydrogen recombines, that the free electron that was stripped off hydrogen by the high temperatures is able to come back to the proton it used to orbit, maybe not the exact proton, and form neutral hydrogen. And when that happens, basically the free electrons go away. All of the electrons, or most of the electrons, are actually in bound atoms in the very superficial layers of the sun rather than being free. And so the pressure support from electrons drops down to something very small. So if I just go back a slide, just as a reminder, the ion and electron pressures both depend on the ion and free electron densities. And really what we are seeing in that plot is just the fact that the free electron density gets very small in the surface layers of the sun because the hydrogen, which is where most of the free electrons come from, is neutral. For hotter stars, that's not the case. The electrons remain free, and the electron pressure remains appreciable right up to the surface layers. Yeah? Yes, you would. But this model does not. This model for the sun does not include a corona. Okay. Even though to actually figure out properties of the solar wind and to model active phenomena of the sun, we obviously do need a model for the corona. The corona has very little effect on the actual internal structure of the sun, because really there's just so little mass out there that it can't do much to change what's going on in the sun's interior. So when we're modeling the structure and evolution of stars, we don't really worry too much about the fact that they may have a corona above their surface. Uh-huh. I would expect first of all, I'd expect as we go through the transition region up to the corona, I would expect both the ion pressure and the electron pressure to shoot up very rapidly at the right-hand end, because the temperature of the corona is so much hotter than the temperatures here. So typically at the surface of the sun, the temperatures are around 5,000 Kelvin, but you go out into the corona and they jump up to maybe 5 million. Okay. To be honest, I don't know. Okay. I'm not a solar astrophysicist. It's going to be somewhere out here, okay? Okay, so we've seen from the case of the sun that the radiation pressure isn't really important, and I guess I've just told you that the electrons, the free electrons, where they're important, behave as an ideal gas. So we can approximate the overall pressure in the sun just as a sum of ion and free electron pressures, and that in turn is just, we can represent as the number of density of ions plus the number of density of electrons times Boltzmann's constant times the temperature. Often a way we will represent the sort of combined effects of ions and electrons together is by introducing something that's incredibly inappropriately named the mean molecular weight. It's mean in a strange sense. It's not molecular because there are no molecules, at least in the sun, and it's not a weight, it's a mass. So it carries on astronomy's proud tradition of terrible nomenclature. But the mean molecular weight, mu, is just the average mass per particle, and the average is over ions and electrons in atomic mass units. So the mean molecular weight times the atomic mass unit is, by definition, the same as the ratio between the mass density, rho, mass per unit volume, and the total particle number density, which is just the number density of ions and the number density of electrons. And using this expression, we can rewrite the equation of state in a form that appears in many textbooks on stellar astrophysics, which is just that the pressure is just density times Boltzmann's constant times temperature over the molecular weight times the atomic mass unit. Okay, so we're going to play a little game now. We're going to see if we can come up with an expression for the thermal energy of a star. We've already got one for the gravitational energy, and this is going to lead us to probably the most important theorem of stellar astrophysics, and one that is so simple to write down that most people, when they first see it, do not grasp quite how important it is. Okay? So we're going to start out by writing an expression for the specific thermal energy of material making up a star. If you think this is an ideal gas, it's monatomic, so each particle has 3/2 kT degree, or has its thermal energy of a single particle is 1/2 kT per degree of freedom. The particles have 3 degrees of freedom because they're moving in 3 dimensions. So each particle has an energy of 3/2 kT. And if we divide by the mean mass per particle, which is just mu times u, we find that the specific thermal energy, the internal energy per unit mass, is just 3/2 times the ratio between pressure and density. With the specific thermal energy, we can then integrate over the mass of the star to get the total thermal energy of the star. That's uppercase U, and it's going to be 3/2. And what we've done here is we've transformed our integral over mass into an integral over radius instead of mass. And it's basically going to be 3/2 times the volume integral of the pressure. I can go through that transformation if people want. Yeah, let's do that. Let's get the chalk out. Ouch. Oh yeah, those are nice, aren't they? Okay, so the integral over the star's mass of the specific thermal energy is this, where I've substituted in that expression for lowercase u. And I just use the chain rule to do a transformation of variables from m to r, and then from my definition of what the mass coordinate is, dm dr is just 4 pi r squared rho. So we can see that rho will cancel this rho, and we'll end up transforming from a mass integral over the specific internal energy to a volume integral over the pressure. So all we've shown really is that the total thermal energy of the star is 3/2 times the pressure integrated over the total volume of the star. Okay, so far, no deep insights. You know, it's just, oh, okay, that's cool. But fun happens when we remember that this pressure integral here can be rewritten using the equation of hydrostatic equilibrium into an integral involving the star's potential energy, and that in turn can be related to the star's total gravitational binding. We've got three things on the screen that we've already encountered. We've already met the gravitational binding energy. We just saw that this integral here is the thermal energy. And we've already met hydrostatic equilibrium, that using the mass coordinate definition, we can translate from a pressure gradient expression into a dP with respect to m expression. So what I'm going to do is I'm going to whip the board up in a moment, and we're just going to go through these expressions and see how we can end up with this rather surprising result. So let's put that up there. And let's just start out with, I'm going to try and show a little bit more discipline with how I use the space on the board this time. So let's just start out like this. Okay. Is that how I want to start out? No, in fact, I'm going to start out slightly differently. I'm going to start out with a definition of the gravitational potential energy, or gravitational binding energy. There we go. And over here, I'm just going to write down a reminder of the equation of hydrostatic equilibrium, but written with respect to mass coordinate rather than radius. So the reason I'm writing this down is I can write this like this. dP dm is 1 over 4 pi r cubed times gm over r. And I can use hydrostatic equilibrium to replace this gm over r with something relating to the pressure gradient. So it's actually going to be 4 pi r cubed dP by dr dr. Okay? So this looks like, I guess, no, that should be m. This looks like an integral I can do using integration by parts. So let's do that. That's going to go up to R now. I've actually switched this, in this integral, I've switched from mass to radius. In this first term, we can actually neglect this, because at the center of the star, the radius goes to 0. And at the surface of the star, we're assuming that there's just so little material there that the gas pressure vanishes as well. So by applying boundary conditions, we get rid of this first term, and we're left with just that the potential energy is minus 3 times the integral of 4 pi r squared p dr. But this is just the volume integral of the pressure over the star. That's exactly what we encountered. If I just do a quick reveal here. Here, okay. So I can also write this as minus 3 times 2/3 times the thermal energy of the star. And that means our final result is that the gravitational binding energy of the star is minus 2 times the thermal energy of the star. So this is known as the virial theorem for stars. Sometimes we encounter the virial theorem when we're thinking about clusters of galaxies, and then we think about velocity distributions and momentum distributions of the particles making up our cluster, and We play all sorts of tricks. This is a different way of doing it for stars, where we're starting from the equation of hydrostatic equilibrium and using the definitions of gravitational binding energy and thermal energy. The virial theorem, I mean, that's probably as simple as an equation as simple of an equation as you can get, but it really has quite profound implications for how stars work. It means that for a star in hydrostatic equilibrium, I don't independently get to determine how much gravitational energy and how much thermal energy it has. The two are intimately linked together. So when one changes, the other must change. And this leads to a rather strange result. So let's first of all define the total energy of a star to be the sum of its gravitational and thermal energies. Remembering from my virial theorem, let's just have it peeking up here in the corner so we can. Remember from our virial theorem that omega is minus 2u, or u is minus half omega. That means that the total energy of the star must be half its gravitational binding energy, and it must also be minus its thermal energy. So the total energy of the star is negative, which means that the star is stably bound. And that's interesting enough, but for me, the really important result here is what happens to a star if it loses energy, okay? So as stars lose energy, so as they radiate away into space, because they're hot and space is cold, that's a net loss of energy from the star. And if the star has no way of replacing that energy, let's say for some reason the star doesn't have any nuclear reactions going on, then the total energy of the star has gone down. And in fact, because that total energy starts out off negative, it's become more negative. So as a star loses energy, its total energy becomes more negative, and then from these expressions here, that must mean its gravitational binding energy must become more negative. That must mean the star has shrunk, so it's contracted. But it also, by this equality here, must mean that the thermal energy of the star must have gone up during this process. So a star with no other sources of energy, as it loses energy into space, will contract, and it will also heat up. That's the thermal energy going up. And this is really the process that allows a protostellar object to start off as this big fluffy ball of gas just contracting, as it radiates its energy away, to continue contracting and to heat up. And this process will continue, this process of contracting and heating up. It's called Kelvin-Helmholtz contraction, until the star reaches the point where nuclear reactions start to occur at its very center, where the temperature is highest. And when that happens, the loss of energy from the surface of the star initially will still be much larger than the rate that energy is being generated in the center. So the star will continue to contract and heat up. But with more and more heating up, the nuclear reactions in the core will run faster and faster and faster, until eventually a point is reached where the energy being generated in the core by nuclear reactions is perfectly matched to the energy being radiated away into space. And at that point, the Kelvin-Helmholtz contraction stops, and the star has reached a steady state with a sort of thermostat that's been perfectly adjusted so that the nuclear reaction rate in the core is tuned to match the loss of energy rate at the surface. And when the star reaches this point, that's when it starts its life as a zero-age main sequence star. That really is the birth point of the star from its sort of early gestation age. And it will then exist in a state of no further contraction or expansion for a long time as it slowly burns its way through hydrogen reserves in the center. So really, the virial theorem leads us to the idea of this Kelvin-Helmholtz contraction, which is how stars get from being big, fluffy things into small, compact, yet hot things. And we'll encounter sort of the reverse of Kelvin-Helmholtz contraction when we talk about stellar evolution tomorrow. So the overall timescale for this process is really just the ratio of the star's total energy to their luminosity. So capital L is the surface luminosity of the star, and it's basically how much energy the star radiates away into space every second. So if we divide the star's total energy by its luminosity, we're going to get something with units of time. And if for the total energy, we just estimate gm squared over r as kind of a ballpark estimate of its gravitational binding energy, then this Kelvin-Helmholtz timescale is gm squared over luminosity times radius. And if we plug in the numbers for the sun, we find a Kelvin-Helmholtz timescale of a few million years. So what that's really telling us is that if somehow nuclear reactions were turned off in the sun would contract and heat up, and the sort of typical characteristic timescale for this process would be a few million years. So this was one of the first pieces of evidence for the fact that, or rather, no, let me turn this around. In the 19th century, when evidence was emerging that the Earth was much older than a few million years, that in fact, from geological evidence, it may be billions of years old, this sort of treatment of Kelvin-Helmholtz contraction was a bit puzzling because it seemed to suggest the sun could only live for a few million years, the Kelvin-Helmholtz timescale, if it was powering itself via gravitational contraction. In reality, of course, the sun's powering itself by nuclear reactions, so it can live for much longer timescales. Okay, so that discussion of energy was really thinking about total energy conservation in the same way when we think about the dynamics of let's say, a multi-particle system. Even if we can't follow the individual particles' energies closely, we should be able to write down a simple conservation law for the whole system. I mean, really, the virial theorem is a first integral of the equation of motion for the system. The equation of motion is hydrostatic equilibrium. We integrated it once. We got a statement about total energy. If we're actually interested in where in the star the energy is and how it moves around, we've got to think in a little more detail. And so here we have the energy conservation equation for fluids. So this is for the internal energy. I'm sure I've got some factors wrong, but let me just explain to you what I think the terms mean. On the left-hand side, this is just the Lagrangian rate of change of the specific internal energy. And it can change due to work done, that's the work term, due to the divergence of a flux of energy that's passing through the fluid. If it's divergent, then that flux is either depositing or removing energy from the fluid. And it can also change due to the release, sort of in situ release or absorption of energy in the fluid. And this might represent, for instance, viscous heating, but it can also, in stars, quite importantly, it represents the release of energy via nuclear reactions. So if we take the same sort of conceit of spherical symmetry, and we can neglect viscosity, and we can neglect time derivatives, so everything's static, we end up with an equation for thermal equilibrium. So let's just see where this comes from. If I take my energy equation and I throw away the left-hand side, because we're assuming we're in a static system, and I throw away the work term on the right-hand side because the velocity is zero, there's no expansion or contraction going on. That just leaves the flux term and the epsilon term. So we have 0 equals, let's write down the flux term. So in spherical symmetry, the divergence operator looks like this. And then we have this epsilon term, and I left out a minus sign there. I'm actually going to introduce an internal luminosity, which is kind of an analog to the mass coordinate. We define our internal luminosity as 4 pi r squared times the local flux. And basically, at any point in the star, lowercase l is a measure of how much energy per second is passing through a sphere that intersects that point. At the surface of the star, the internal luminosity then goes over to the total luminosity of the star. So with this definition of L, I can rewrite this expression here as and I should have had a rho there. 1 over 4 pi r squared rho times d by dr. 4 pi, I guess it's going to be 4 pi r squared f, and that's just going to be L. And I'm going to recognize that this term here is the same as dm. Remember, we're physicists, so derivatives are just fractions of two different numbers. And so from this, if I move this term over to the left-hand side, the gradient of the internal luminosity with respect to the mass coordinate is just given by epsilon. And this epsilon, since I've said I'm neglecting viscous dissipation, I'm actually going to explicitly make clear that this is the energy release rate per unit mass due to nuclear reactions, eps-nuc. And so this is our energy conservation equation in the inviscid, spherically symmetric, static case. And so for stars that obey this equation, we say that they're in thermal equilibrium. There's no heating up or cooling down going on. They're in a nice thermal equilibrium. And here's our definition of the internal luminosity. Okay, so let's take a look at what this looks like in the sun. So this is a plot of how well we satisfy the thermal equilibrium constraint in the sun. I'm plotting both the gradient of internal luminosity with respect to mass and the nuclear energy release rate as a function of radius in a model for the present-day sun. The two curves should lie on top of each other. Again, I've probably screwed up a little bit in calculating the luminosity gradient in Python, so they don't quite lie on top of each other, but I'm not really that worried about it. The takeaway from this graph is really seeing where eps-nuc is large. So in the core of the sun, let's say in the inner 20% by radius of the sun, that's where almost all of the nuclear energy is being generated, and there's almost no energy generated in the rest of the sun. And that's because the temperatures really just aren't high enough there for nuclear reactions to occur. For the hydrogen burning reactions that take place in the sun, there's kind of, I'll get to you in a moment, a limit on the temperature. You've got to be above maybe 5 to 10 million Kelvin or nothing happens.
Yeah, I was just going to ask where you're defining the core, because I think you said earlier it's like 0.1.
It's kind of nebulous because there isn't a sharp division between regions that undergo nuclear reactions and regions that don't. If I drew the line at point 0.1 here, we could see that maybe that gets us halfway up to the peak burning rate. But really, there isn't a hard and fast definition. Now, it's kind of different for more massive stars because they have convection going on in their cores. And often we will define the extent of the core as the extent of the region where mixing is occurring due to convection. But in the case of the sun, there is no convection going on in the core of the sun today.
Yeah, so with a radiative core, you're basically just setting some limit for nuclear energy generation.
Yes, I mean that.
In this case, that's like order of magnitude 4.
Yeah. I mean, one way of turning your question around would be, how does the sun know where its core stops? And I guess the answer is it doesn't really care. When we talk about the core of a star, sometimes we're quite specific, and sometimes it's just a vague, the stuff near the center.
Yeah.
Okay?
Yeah, I know it's quite specific for massive stars.
Yeah, that's right. Okay, so let's play the same game that we played with hydrostatic equilibrium and ask over what sort of timescales can we expect departures from thermal equilibrium to occur. So suppose in a star, nuclear reaction stopped suddenly, so we drop the epsilon term from the full energy conservation equation, and we end up with an equation that looks like this, and we can just use order of magnitude estimates, replacing U by the total thermal energy of the star, replacing L by the total luminosity of the star, replacing U times M by the with the total energy of the star. The amount of time it would take for the thermal structure of the star or the sun to change significantly is given by the thermal time scale, which is just the ratio of the internal energy of the star divided by the luminosity, but that's just via the virial theorem, more or less the total energy of the star divided by the luminosity, and that's just the Kelvin-Helmholtz time scale that we already encountered. So what this is really telling us is that if nuclear reactions cease tomorrow all throughout the sun, it would take us a few million years to notice it. Now, that's a long time by our standards, but by the sun's standards, and the sun will be burning hydrogen in its core for another 5 billion years, that's just a blink of an eye. So throughout the sun's hydrogen burning phase, we can assume to a very high degree of accuracy that it's in perfect thermal equilibrium. Only when it goes through evolutionary phases that are shorter than the Kelvin-Helmholtz timescale do we have to worry about departures from thermal equilibrium. In just the same way that only when it goes through departures or phases of evolution that are shorter than the dynamical timescale do we worry about departures from hydrostatic equilibrium. So this sort of discussion of timescales really underscores some of the challenges we face when modeling the evolution of a star, because there are some processes in a star that can take place on a timescale of an hour, and there are some processes that can take place on a timescale of 10 billion years. And so we have not only a very big contrast between or not only a very big dynamical range between, let's say, the density at the center of a star and the density at the surface, but we also have a huge dynamical range in timescales. Unfortunately for us, for most parts of a star's evolution, these timescales kind of fall into a strict hierarchy, and they're well separated in that hierarchy. So the dynamical timescale is short, of order an hour, the thermal timescale's intermediate, of order a few million years, and then the nuclear timescale, how long it will take a star like the sun to burn through its nuclear reserves, is on the order of 10 billion years. So these timescales are very, very well separated, and as a consequence, we can often ignore things taking place on short timescales if we're focused on changes over long timescales. Okay, so the energy conservation equation tells us that energy must be conserved in a star, but it doesn't tell us how the energy moves around. To do that, we need some sort of prescription for the transport of energy. In stars, there are three main ways energy can be transported. One is by radiation, basically the diffusion of photons from regions where the star is hot to regions where it's cold. Another one is conduction, but I'm not really going to talk about conduction much because it turns out it can be treated with exactly the same formalism as radiation. And then the third one is convection. And convection is tricky. We still don't have a comprehensive theoretical formalism for treating convection. It's one of the biggest unsolved problems in the study of fluids. In stars, we get away with sort of approximate treatments that maybe capture some of the important physics, but basically they're hacks, they're tricks that allow us to fudge the correct behavior. And we know it's the correct behavior because our models for the sun kind of agree with the sun, but whether our fudge factors agree for stars in other phases of evolution is still kind of an unsolved problem. I'm going to start out by talking about radiative energy transport. So this is just photon diffusion. And the equation governing this is just a diffusion equation that tells us that the flux, the energy per unit second per unit area, of energy due to photons just depends on the gradient of the photon energy density, which is radiation constant times temperature to the power of 4. And then out front, we get a diffusivity, which is, I mean, this term here is basically 1/3 divided by the mean free path of photons in the medium. And often we represent that mean free path as an opacity, a cross-section per unit area, times a mass per unit volume, the density. So this is just the basic radiative diffusion equation in stellar interiors, and we can rewrite this in terms of the internal luminosity L. It's very straightforward. If we first of all just specialize that equation to spherical symmetry, our diffusion equation, in spherical symmetry, flux is minus 1/3 kappa rho times d by dr of at to the 4. And then I'm going to use the chain rule. Just to expand this out, so it's going to minus 4ac t cubed over 3 kappa rho times dt dr. And then if I multiply this whole thing by 4 pi r squared, I'm going to convert the flux into the internal luminosity. So we're going to get a 16 pi r squared act cubed over 3 kappa rho times the temperature gradient. Now, hopefully, that's what I've got here. I think it is. Okay? And it's important that you see the minus sign here. So the luminosity or the flux tend to flow down the temperature gradient from hot regions to cold regions. So this looks like an equation that tells us what the radiative luminosity, and I've put a little sort of subscript on my L to remind me that this is just the luminosity, or the energy transport rate via radiation. The way I've written this, it makes it look as though this is a recipe for calculating what the luminosity is given the temperature gradient. But in reality, it's kind of a recipe for calculating what the temperature gradient needs to be in order to transport a given luminosity. And what the luminosity should be is something that we get from solving our thermal equilibrium equation. I think one of the challenging things when one's playing around with the equations of stellar structure is coming up with a cogent narrative of how to read equations and decide which is the chicken and which is the egg, which is the dog and which is the tail. Who's in charge? Is the temperature gradient setting the luminosity, or is the luminosity setting the temperature gradient? And I just argue that this equation is the temperature gradients, the luminosity deciding what temperature gradient it needs. There are many different ways to argue it back and forward, and in fact, none of them are correct, and all of them are correct, in the sense that a star finds a way to evolve towards an equilibrium state that satisfies all of these equations. If the temperature gradient's wrong, but the luminosity's right, then not enough energy will get transported, and different parts of the star will heat up, and that'll change the temperature gradient until all of the equations are satisfied. Basically, the star finds a way to evolve towards an equilibrium state that satisfies all of the governing equations. And sometimes it's really difficult to decide what's causing those changes. It's a game that stellar astrophysicists like to play a lot, especially in trying to figure out why stars become red giants. I might say something about that tomorrow. Okay, so let's have a look at radiative energy transport in the sun. So this graph, it's our model for the present-day sun. We've got two curves plotted as a function of radius. The solid blue line is the luminosity. This is the total luminosity, the total amount of energy per second passing outwards in the star at that radius. And the dashed line in orange is the radiative component of that, the component of that total luminosity that's transported via the diffusion of photons. So let's just focus on the blue line first. The blue line starts off at 0, and it rises up close to 1, and this is in units of the star's total luminosity. So basically, it goes from 0 up to the surface luminosity, very close to the center of the star. And this is really because all of the nuclear reactions are going on here. So where there are lots of nuclear reactions going on, dl by dm is large and dl by dr is large. And then when we run out of nuclear reactions, basically the luminosity is already at its surface value, and it's just making its way out through all of this superficial stuff that isn't generating any energy. Now, the radiative luminosity pretty much follows the total luminosity in the star until we get out to here. And then it suddenly drops like a rock, and it becomes almost 0, and then it suddenly changes its mind and rebounds up and rejoins the total luminosity. So what on earth is going on here? Any thoughts? Convection. There's a great big convection zone at the surface of the sun. In fact, not at the surface, it's actually the outer 30%. It starts just here, which is about 70% of the sun's radius. So really what's happening is, if we go back to the radiative diffusion equation, the reason why the radiative luminosity drops like a rock in that convection zone is that convection starts transporting energy in the star. And when we transport energy from a hot region to a cold region, we tend to smooth out the temperature gradient. We tend to make it less steep. So convection is secretly messing around with that temperature gradient in the diffusion equation. basically trying to make the temperature gradient as shallow as possible, and that means that photons have a hard time diffusing, because when the temperature gradient goes away, photons can't diffuse at all, okay? So that's what's causing the sudden drop in the radiative component of the luminosity. And if we take a look at the actual values for the temperature gradient, we can see that for ourselves. So what I'm plotting here are a couple of curves that show the temperature gradient, but kind of represented in a very idiosyncratic way. Previously, when we've written a temperature gradient, I think I wrote it on the board, we've written it as dt by dr. But what's nasty about that is, it has units of kelvins per centimeter, and it's got a nasty bit of CGS in there, and also it's, really, what is a Kelvin per centimeter? I want something dimensionless. So the way we like to talk about temperature gradients in stars is the logarithmic temperature, the logarithmic derivative of temperature with respect to pressure. So here, in a sense, we're using the pressure as the independent variable. This is a quantity that's always positive, almost always positive. Pressure always decreases outwards. Temperature generally decreases outwards. So we expect both the numerator and the denominator to both be negative, and therefore the overall thing to be positive. And it's just a dimensionless way of measuring temperature gradients. The solid line in blue shows us the temperature gradient we would get if there was just radiative diffusion in the star, okay? And as we go out to the outer layers, that temperature gradient becomes very, very steep. So in those outer layers, in order to transport all of the star's luminosity via radiative diffusion, there would have to be a very steep temperature gradient. In reality, what happens is that steep temperature gradient kind of starts convective fluid motions going. We know that convection starts up when there's a load of hot stuff down below and a load of cold stuff up top. The hot stuff tends to rise and the cold stuff tends to sink, and we get convective circulations going on. So when the convection kicks in, it takes this temperature gradient that radiative diffusion alone might want to set up, and actually brings it all the way back down to here, shown by the orange dashed line. So the orange dashed line is the actual temperature gradient in the star, and the blue line is the temperature gradient that would exist if radiation alone had to transport all of the energy. So if convection could be artificially suppressed. And we can see how the onset of convection actually pulls the temperature gradient down much shallower. And that's the reason in the previous slide, it was that suppression of that temperature gradient that the radiative flux then drops off. Okay, so let's talk a little bit about under what circumstances we can actually expect this convection to set in. Energy transport by radiation is always there in a star. Whenever there's a temperature gradient, and that almost always is, apart from at the very center of the star, there's going to be the transport of energy by radiation. But convection is kind of different. It doesn't always happen. There has to be a steep enough temperature profile in the star in order for convective motions to start up and carry on. And in fact, I said temperature gradient, but really there has to be a positive gradient of entropy with respect to pressure. So as I go from the, what that means, remembering that pressure decreases outwards, is as I go from the high pressure center to the low pressure outer regions, I must go from high entropy to low entropy in order for convection to start. So basically, I must go from hot stuff at the bottom to cold stuff at the top, convection. So whenever this inequality is satisfied, whenever the material down towards the center of the star has more entropy than the material in the outer layers, then convection will naturally start to occur. This is the sort of rigorous way of expressing the criterion for convection, but in reality, we can actually rewrite this in terms of an inequality involving temperature gradients with respect to pressure rather than entropy gradients. Now, depending on the time, what the time was, I was going to go through a full derivation of this, including the triple partial differential formulae from thermodynamics, but we've got 20 minutes left, so I'm not going to inflict that upon you. what I want to emphasize about this inequality is, so if we satisfy this inequality at a point in a star, convection will occur at that point. This is the criterion for convection. And the two quantities on either side of the inequality, it's important to realize, are quite different beasts. Okay, so on the left-hand side, this is the rate of change of temperature with respect to pressure, as you would measure in the star. If you take 2 points that are near each other, and you measure the pressure difference between them, and measure the temperature difference, and then take the ratio, because we're physicists, not mathematicians, then we would get the physical or structural temperature gradient. How fast is temperature changing in my star with respect to pressure? So on the left-hand side, this really depends on the structure of the star. On the right-hand side, however, this is a thermodynamic gradient. This tells us how much the temperature would change if I changed the pressure in a way that kept the entropy the same. So this is for an adiabatic process, the rate of change of temperature with respect to pressure. And it tells us nothing about the structure of the star. It tells us something about the thermodynamic state of the fluid making up the star. So on the left-hand side, something that depends on the star's structure. On the right-hand side, something that depends on the thermodynamic properties of the fluid. For an ideal monatomic gas with no ionization effects, the quantity on the right-hand side is 2/5. Okay? So what this is really telling us is that anywhere in the star where d log T by d log P exceeds 2/5, we should expect convection to occur. And that's really what we see. So let's take another look at our solar model. Actually, no, let's not. We've got a surprise slide, at least a surprise for me. This is it's funny because I spent more time on this slide than anything else. This is a recipe for, if we're building a stellar model, to actually decide where convection occurs. Because there's kind of a sort of iterative procedure to deciding where convection occurs. Because to start off with, we don't really, if we look at this inequality here, this tells us, well, if the temperature gradient exceeds this, then we're going to get convection. But we don't actually know what the temperature gradient is to start off with. That, in fact, is what we're trying to calculate. So this is my little flow chart for figuring out where in a star convection will occur and how to calculate that temperature gradient. Okay? So the first thing we do is we evaluate these two quantities here. This is the temperature gradient that we would get in the star if energy was transported by radiation alone. And it's something that we can calculate just from the radiative diffusion equation. So just by knowing the internal luminosity throughout the star and other things like the opacity and the density, we can calculate this. And stellar astrophysicists often like to write this as grad rad. They'll call it grad rad or nabla rad or del rad. And they get to reuse the del symbol because they're doing everything in 1D. So they have no use for vector calculus. So they get all of these symbols that are freed up. It's kind of cool. The second term is just this thermodynamic derivative, the rate of change of temperature with respect to pressure at constant entropy. And this is written as del or nabla or grad ad, and is known as the adiabatic temperature gradient. So these two things are known as the radiative and adiabatic temperature gradients. And the first game we play is, okay, so we're going to start off assuming all energy is transported in the star by radiative diffusion. Then at every point in the star we say, is grad rad greater than grad ad? And if the answer is no, so we're down here, then no convection, which means that all of the energy should be transported by radiation alone. We're good, we're home free, we're done. And then that means that the actual temperature gradient in the star should be equal to the radiative temperature gradient. And we're finished. If the answer to this question, however, is yes, if grad rad is greater than grad ad, then we've kind of got an inconsistent situation. We started off assuming radiative transport alone, but then we found radiation transport alone will give a temperature gradient that's steeper than the adiabatic gradient, so convection should start. So convection is going to start, and we have to make an estimate of whether the convection is efficient or not. So by efficiency, what I mean is, how well will the convection suppress the temperature gradient below what it would be if there was just radiation alone? If it's very inefficient, it won't suppress it at all and will end up in the same limit as no convection. So that's our answer there. But if the convection is very efficient, then it will push the temperature gradient down as low as it possibly can without shutting off the convection altogether. And so the actual temperature gradient will go to grad add. Now, actually deciding between these two cases is where all of the nastiness in treating convection comes in. That's where we need a full model for convection. And in stars, we usually rely on something called mixing length theory that some of you may have heard of. And it's this kind of hand-wavy approach that includes an adjustable parameter that's calibrated against the sun. And that's how we handle convection. But one day, perhaps, there will be a more comprehensive theory that will allow us to decide what the actual temperature gradient should be when convection is occurring. Okay, so let's take a look at convection in the sun. I am plotting the radiative temperature gradient, the adiabatic gradient, and then the actual temperature gradient that results after I've decided whether there's convection or not, and so on. And I'm plotting it against fractional, or 1 minus the internal mass over the total mass. I've got my axes back to front, so I should add that the center of the star is here, okay, and the very superficial regions are out here. And I've used this as my axis because I really wanted to emphasize what goes on near the surface of the sun. So right down in the center of the sun, we have, first of all, we look at grad rad and grad add. Grad rad is underneath grad add, so there's no convection. Energy is just transported by radiation alone. As we get out to this point, however, the two curves switch around. Grad rad goes above grad add, so the blue above the orange, and convection must set in. So even though this appears way over on the right of the plot, we're already out to the 70% by radius in the sun. Because remember, that's where the sun's convection zone starts. So everything from here outwards is the outer 30% by radius of the model. So to start off with, in this convection zone, from here all the way over to here is the surface, is the outer convection zone of the sun. You'll notice that it doesn't extend all the way out to the surface of the sun. There's a thin radiative layer. I'll get onto that in a moment. But over this convection zone, for the most part, the actual temperature gradient, shown in purple, is at its lowest possible or shallowest value. So this is efficient convection. Remember, convection can choose to set the purple line anywhere between the orange line and the blue line, which goes off the top of the plot. And it's choosing to set it at the bottom of the envelope. So that's efficient convection. It's making the temperature gradient as shallow as it can be. But as we approach the upper part of this convection zone, the convection starts to get inefficient, and it's no longer able to push the purple line all the way down to the orange line. In fact, just here, it can't really decrease by much at all below the blue line. And so right out here is very, very inefficient convection, which is almost the same as no convection at all. And then we transition over to a radiative zone in the surface layers, okay? The behavior down here isn't really that sensitive to how we model the convection in detail, this mixing length theory, this approximate theory we use. But the behavior out here is quite sensitive to the assumptions we use in how we actually model a convection. And if we get that wrong, our approximate treatment, then we can potentially get a star that's too small or too big by a significant and measurable amount. And here, where the purple line goes below the blue line, I have no idea what's causing that, because that shouldn't be able to happen. So, okay, so we're now at a point, after 80 minutes of me gibbering, to actually write down the equations governing stellar structure. So this is the full set of equations, well, the full set of differential equations that govern the structure of stars. There are only 4 equations. They're all first order, ordinary differential equations, no partials, but they are nonlinear, and that kind of makes them a little bit fruity to solve. We've got hydrostatic equilibrium, which tells us that the pressure gradient is in balance with gravity. Just the definition of the mass coordinate, which links the mass coordinate to the radius and the density. The energy conservation equation that tells us the luminosity gradient must match the energy generation rate. And then energy transport, which tells us that the actual temperature gradient, dl and T by dl and P, must either be grad rad in radiative zones or somewhere between that should be grad ad and grad rad in convection zones. And those are our 4 basic equations of stellar structure. So our task in coming up with the structure of a star is to solve these equations. Now, we need a little bit more than that to come up with solutions. We do need boundary conditions to make it a well-posed problem. So at the center, by definition, our mass coordinate goes to 0 and our radius goes to 0, unless we have a point mass of energy, our luminosity should go to 0 as well. At the surface, the mass coordinate goes to the overall mass of the star, and that's a quantity we actually get to pick when we're coming up with a model. And then we need a couple of boundary conditions to apply to the temperature and pressure, and typically we come up with something that we derive from theory of stellar atmospheres, but I'm not going to go into that in any detail. So as a very first approximation, and this is kind of wrong but not terribly so, you can assume that the temperature and pressure go to 0 at the surface of the star, because you're basically transitioning into cold empty space. As well as those differential equations and boundary conditions, there's the question of microphysics, which I talked about a little bit in focusing on the equation of state. But this is where a lot of the blood, sweat, and tears comes in putting together models for stars, is actually getting microphysics equations that describe the universe as it is, not some simplified sort of approximation to it. So firstly, something I haven't really talked about that much is that we need some way of specifying the actual chemical makeup of stellar material. When we talk about chemical makeup and chemical species, we're just talking about isotopes, really. There's no chemistry going on here, but I guess we like to mislabel things all the time. So at any point in the star, the composition of stellar fluid is specified by a set of mass fractions, which basically, if we have a 1 gram sample of stellar material, it's the fraction of that gram that's made up by each isotope. So we can have a mass fraction for hydrogen, one for deuterium, one for helium-3, one for helium-4, and one for all of the other elements. And how many elements we actually want to explicitly think about depends on what we want to do with our model. If we're only interested in making a model for the hydrogen burning phase of the sun, we really don't need to include the rare earth elements in our description of the sun's abundances. But if we're worried, for instance, about maybe nucleosynthesis in late stellar evolution stages, then that might become more important. Once we've got a set of abundances, then our microphysics really comes down to specifying 3 functions that describe the dependence of the opacity, the cross-section per unit mass of stellar material, as a function of its density, temperature, and composition. And when I write xi, that basically means a whole set of numbers that specifies the mass fraction of all of the different elements making up the star, subject to the constraint that mass fractions must always add up to 1. So we've got an opacity function. We've got our equation of state that tells us how to calculate the pressure, given the density, the temperature, and these mass fractions, and then some recipe that tells us how to calculate the nuclear energy generation rate, given the density, temperature, and abundances. So once we've got our microphysics in place, we've got our boundary conditions, and we've got our 4 differential equations, we're in principle in a position to solve the stellar structure equations. To do this, we typically discretize the star, or basically come up with a discrete representation of the star that we're modeling. And there are different ways of doing this, some based on finite differences, some based on finite volumes. I'm going to talk about finite volumes. We do finite volumes on kind of a staggered grid where some quantities are basically cell averages and other quantities are sort of point samples at faces. So we represent density, temperature, and abundances as cell averages. And by a cell, I actually mean a spherical shell in the star. Here, they're labeled by an index K that, for some strange reason, always goes inwards from the surface, which is kind of annoying, but that's how people do things. And then quantities that are defined at faces include the mass coordinate, the radius coordinate, and the internal luminosity. And then dm is just the difference between the mass coordinates of adjacent faces. It's basically the mass of the shell. So with this finite volume sort of representation of a star, we can actually take each of the differential equations governing the star and discretize them, replace them with some sort of finite difference or finite volume equivalent. So for hydrostatic equilibrium, this is one way in which we might discretize it. So we're replacing the derivative of pressure with respect to mass with some finite differences between the cell average pressures in adjacent cells. And this is some representation of the change in mass coordinate between them. And then on the right-hand side, this is the gravitational term at the face between the two cells. And what's important to realize in this is that the pressure itself is not actually stored in our finite volume representation. It's something that we actually have to look up implicitly from our equation of state, which depends on the pressure in the cell, the density in the cells, the temperature, and the composition. Actually putting together these finite difference representations typically involve going to those microphysics modules and finding out what the pressure is for a given density and temperature and so on. So how do we solve all of these wonderful finite difference equations? We can make a finite difference equation like this for every interface between every pair of cells, and for all of the different differential equations. We've looked at the 4 differential equations for the stellar structure, and there will also be algebraic equations that represent the boundary conditions, and we can represent these generically as a whole set of implicit nonlinear equations that depend on the density in the cells, the temperatures, the abundances, the mass coordinates, the radii coordinates, and the luminosities. And these are all a big set of implicit equations with a big fat 0 on the right-hand side. Here, J indexes over all of the discretized equations, K is indexing over cells and cell faces, and I is indexing over chemical species. All of these equations can kind of be thrown together into a really big, gross matrix representation that we solve then by Newton-Raphson iteration. So Newton-Raphson iteration for scalar implicit equations basically is just a way to take an initial guess as to a solution of an implicit equation and improve it given an estimate for the gradient of the implicit function. For this sort of problem, since we're dealing not with a single unknown but multiple unknowns, we can write the Newton-Raphson method like this. So if we have an estimate for a solution to our system of equations called yn, and this is a vector of unknowns, and the vector contains the density, temperature, and so on in each cell, then we can get a better guess, yn plus 1, by correcting yn with this quantity here, which is basically a big Jacobian matrix inverted and then multiplying the current guess. And this is an iterative approach to solving the equations. And hopefully, if we apply multiple iterations, we'll converge to some kind of a solution. If this Jacobian matrix can be absolutely huge, and matrix inversion is something that can be very time-consuming. In general, this would be something that would be far too difficult to do computationally, but it turns out that the Jacobian matrix is typically block tridiagonal or similar, so it's a very sparse matrix, and we can take advantage of this, both to cut down on the amount of storage we need to represent this matrix, but also to cut down on the computation time we need to invert it. If we just treated this as a dense matrix and naively tried to store it, we would need, this is the number of cells, this is the number of species, and the 4 is because we've got 4 extra variables on top of our chemical abundances to store the state of the material. Naively, storage goes as nk squared times ni squared. If we exploit sparsity, we can save a whole factor of nk, so the number of cells in our model, which typically might be 1,000, so that's a factor of 1,000 savings in storage. That's pretty neat. For solution, the savings get even better if we go from naive to sparse, and there are various parallel matrix inversion routines or matrix factorization routines. Here, NP is the number of processes that can make things very efficient. We really make very big use of the sparse structure of this Jacobian matrix. I'm almost out of time. I can save this discussion until tomorrow. I'm going to finish up by giving you a little bit of homework. All of the examples you've seen today were calculated using a piece of software called MESA, which stands for Modules for Experiments in Stellar Astrophysics. This is an open source code for doing 1D stellar evolution. It was originally discussed in a paper by Bill Paxton in 2011. Since then, there have been a number of instrument papers, as we call them, that discuss improvements to the code. I'm on all but the first paper, and I've been involved in the project since 2012. It's a very big project that brings together all sorts of fun bits and pieces, including state-of-the-art opacities, equations of state, nuclear reaction rates, and things like that. And as I've said before, that's really where the blood, sweat, and tears lies in putting together a stellar structure and evolution code. It's written in modern Fortran, or at least parts of it are, although some of it's the best C written in Fortran I've ever seen. It's very well documented and has summer schools every year. So every August, around 50 students get together in Santa Barbara to learn how to use the code. And you're going to get an abridged version of that tomorrow afternoon in the hands-on session. Your assignment for tonight and tomorrow morning, should you wish to accept it, is to see if you don't already have Mesa running on your laptops, if you can download and install it. And then tomorrow afternoon, we'll go through a simple run, maybe build a model for the sun, and just see the basic functionality of the Mesa code. What's kind of nice about it is, this is a 1D code. There's a lot of fun microphysics in there, but since it's a 1D code, it can run quite nicely on laptops. All of the models I've been showing today will run on the laptop I'm presenting on. So have a shot at downloading it. I'll leave this up on the screen as we go into the break. And we'll have a go at running it tomorrow afternoon. In my talk tomorrow before the hands-on session, we're going to talk a little bit about stellar evolution. So right now, we've just written down the equations of stellar structure, and we've got no idea why stars change over time. And so we're really going to come up with an idea of that in tomorrow's session, and also talk about the various distinct stages of evolution that stars pass through on their way from birth to death. Okay, that's it. Thanks.